Linear models. In this video, you'll learn how to describe the rate of change in y-intercept for a linear model that represents a situation. You'll also learn how to draw a linear model that fits the data well and use the linear model to estimate values that we want to find. So a linear model is an equation that represents a trend in data. We can analyze slope and intercepts to understand real-world relationships. Predictions can be made using this model, but should be reasonable based on the context. So let's look at an example of a linear model. A movie theater has a special going on right now. They charge for each ticket plus an online service fee. This graph represents this special, where X represents the number of tickets and Y represents the total price. What is the Y-intercept and what does it represent? We can see the Y-intercept right here at 0, 1. So since our y-intercept happens at 0, 1, that says that our x value would be 0, so we'll have 0 tickets, and our price is 1. So this tells us that for 0 tickets, the price will be $1. What is the slope and what does this represent? So when we look at how our points move from one to the next, it goes up 1 over 1. So our slope is 1 over 1, or just positive 1. This tells us that as the tickets increase by 1, the price also increases by 1. Using this model, how much will you pay for 10 tickets? So we can represent any linear model by using slope-intercept form, where y equals mx plus b. We know that our slope is 1, so we'll replace m with 1. Our y-intercept is also 1, so we'll replace b with 1 as well. Now we can use this model to find how much we'll pay for 10 tickets. We'll replace x with 10 and then evaluate the function. 1 times 10 gives us 10, and 10 plus 1 gives us 11. So for 10 tickets, we'll pay $11. Now let's look at scatter plots. Scatter plots display data points to show relationships between two variables. The line of best fit is a straight line that approximates the trend of the data. Not all points will lie exactly on the line though, because real-world data can be messy. So let's look at some scatter plots. The scatter plot shows the number of minutes people had to wait for service at a restaurant and the number of staff available at that time. A line that models the data is y equals negative 1.62x plus 18. Where y represents the minutes of wait time and x represents the number of staff available. The slope is negative 1.62, but what does that mean in this situation? Well, we know that slope is the rate of change between the y and the x variables, and we know that y was the wait time and x represented the total staff. So if our slope is negative 1.62, then this tells us that the wait time decreases by 1.62 minutes for each added staff. The y-intercept is 0, 18. What does this mean in this situation? So since we know that x is 0 and y is 18, then the wait time is 18 minutes when there are 0 or no staff. Even though this fits our model and it's accurate, it doesn't really make sense in our situation, because if there was no staff, there would really be no wait time because we would never get any service. So it's important to just always make sure that these make sense in the situation. Now let's use the line of best fit to find the wait time if there are 10 staff available. So we'll bring down our equation they gave us, and we'll replace x with 10, since we want to know when 10 staff are available. Now we'll evaluate. Negative 1.62 times 10 gives us negative 16.2. When we add that to the 18 that we have, we get that y is equal to 1.8. So if there are 10 staff available, then our wait time will be around 1.8 minutes. Now let's use the line of best fit to find the amount of staff available if the wait time is 15. So we'll still take our original equation, but this time we're going to replace y instead of x. So y will become 15 since that represents the 15-minute wait. Now let's solve for x to figure out how many staff are available. We'll start by subtracting 18 from both sides. This gives us negative 3 is equal to negative 1.62x. Now we'll divide by the coefficient of x to get it by itself. This gives us x is equal to 1.85. So this means that there were about 1 to 2 staff available if the wait time was 15 minutes. Here's another example. A taxi driver records the time required to complete various trips and the distance for each trip. The line of best fit is given by the equation y equals 0.467x plus 0.417. We'll use the line of best fit to find the distance for a trip that takes 20 minutes. So we'll take the equation that they gave us, and we'll replace x with 20 since x represents the minutes. Multiplying 0.467 times 20 gives us 9.34. When we add that to the 0.417 we get a total of 9.757. If we plot this on our graph where x is 20 and y is 9.757, it follows that trend that the line fits, so this is accurate. Now let's use the line of best fit to estimate the time for a trip that's 6 miles long. So we'll take our equation again, and this time we'll replace y with 6, since the y variable represents the miles. So we'll solve for x to find out how long it took. We'll start by subtracting 0.417 from both sides. This gives us 5.583 is equal to 0.467x. Now we'll divide by our coefficient of x. This gives us a final answer of x equals 12. And when we plot the point 12.6 on our graph, we can see that it lines up with the rest of our data, so this is accurate. Now let's recap what we've learned. Scatter plots display data points to show relationships between two variables. A line of best fit from a scatter plot can help us analyze the data and model future values. While a line of best fit can predict values, we always have to make sure that it makes sense in terms of the context.